Have you ever stopped to wonder how your phone can spot your face in a photo, or how a smart speaker picks out a single word from everything you say? Well, it all boils down to a computer's ability to find a pattern. And today, we're going to pull back the curtain on the surprisingly simple, but really powerful idea that makes it all work: template matching.
Right, so think about it. Facial recognition, voice assistants, at their core, they're all doing the same thing. They're trying to find one small known pattern inside a much bigger, much messier chunk of data. So how on earth does that search actually work under the hood?
The answer is a classic technique called template matching. And honestly, the idea itself is wonderfully simple. You've got a template, that's the thing you're looking for, and you've got a test pattern, that's the big picture you're searching in. The whole game is just to find the one spot where that template fits best.
So here's our game plan. We're going to start with the most basic, straightforward approach you can imagine. Then we'll get clever and learn some tricks to make things way faster. After that, we'll tackle what happens when things aren't a perfect match. And finally, we'll see how all of this applies to the world of sound.
Okay, let's start at square one. The absolute simplest case. We're looking for a perfect pixel-for-pixel match. Let's say we have a tiny picture, our template, and we want to find that exact same picture inside a much larger one. No tricks, no rotations, no size changes, just a perfect copy-paste.
The go-to tool for this job is something called cross-correlation. And it's pretty much as simple as it sounds. You literally just slide your little template picture over the big one, moving it one pixel at a time. And at every single position, you calculate a similarity score to see how well the pixels line up.
And this breaks it down perfectly. You take your template, you slide it over the big image, left to right, top to bottom, hitting every single possible spot. At each one, you do a quick calculation for that similarity score. And once you've checked everywhere, you just look for the place with the highest score. Boom, that's your best match.
So what does this similarity score actually look like? Well, we use what's called a normalized score, where a perfect one means a perfect match. This is really neat because it means the pattern of pixels is identical, even if one image is a little brighter or darker than the other. So our goal is super simple. Find the spot that gets us closest to a perfect one.
But here's the catch, and it is a huge catch. This method is slow, like painfully, incredibly slow. For a modern high-resolution image, we are talking about billions and billions of calculations. It's the brute force approach, and for anything that needs to happen fast, like real-time video, it's just not going to cut it.
So if checking every single pixel is way too slow, what's the plan B? Can we find a match that's good enough without all that heavy lifting? Oh, absolutely. It's time to work smarter, not harder. Let's look at some clever shortcuts.
Let's just put these two ideas side by side. The exhaustive search we just talked about? It's methodical, sure, but it is slow. A heuristic search, on the other hand, is fast and smart. It doesn't bother checking everywhere. It uses clever shortcuts and educated guesses to zero in on the answer. It might not guarantee the absolute single best pixel, but it'll find a fantastic match in a fraction of the time. So let's look at a couple of these smart approaches. First, the logarithmic search. Think of this like playing hot or cold. You start by checking just a few points that are really far apart. When you find a promising area, a warm spot, you zoom in and search again with a finer grid. You just keep repeating that until you find the match. Then you've got hierarchical search. This is different. You shrink both images way down, find a rough match on the tiny, blurry versions, and then use that location as a starting point for a much more focused search on the full-size images. These are the kinds of tricks that make real-time tracking possible.
Okay, so we've figured out how to make our search faster. But what about another real-world problem? What if the object we're looking for isn't perfect? What if it's been rotated or stretched or warped a little bit? Our rigid little template just isn't going to work anymore.
And as this quote from our source material puts it so well, once the situation gets more complicated, once things are rotated or deformed, that old sliding picture method completely falls apart. We're going to need a whole new approach. And the solution is so clever. It's called a deformable template. So instead of thinking of our template as a rigid block of pixels, we imagine it's more like a flexible outline, almost like it's made of a rubber band. The algorithm can then mathematically stretch, bend, and twist that outline to see if it can fit a shape in the image.
Now, here's where it gets really smart. It's a balancing act. The algorithm is trying to minimize two different costs at the same time. The first is the matching energy. Think of this as how well the template fits the edges of the shape in the image. The second is the deformation energy, which is basically a penalty for how much it had to stretch and warp the template to make it fit. The goal is to find that sweet spot, a really good fit, without having to deform the template into something unrecognizable. This is so important for things like medical imaging, where you're trying to find organs that change shape from person to person.
All right, so far we've been completely focused on images, on things we can see, but template matching is so much more powerful than that. So now let's take all these ideas and leap into a totally different domain, the world of sound.
Let's pose a new problem. How do we find our template, say a recording of the word hello, inside a much longer recording, like a whole conversation? The tricky part is that people talk at different speeds, right? A simple cross-correlation is useless here, because my hello might be way shorter or longer than yours.
Well, the first thing we have to do is process that audio. We can't just compare the raw sound waves. So we chop up the audio into these tiny little overlapping chunks. For each of those little pieces, we analyze its unique sound signature, basically the mix of frequencies, and create a kind of digital fingerprint. And just like that, we've turned a messy continuous sound wave into a neat sequence of symbols that a computer can actually compare.
Okay, so now we have two sequences of these fingerprints, our template word and the long recording. To compare them, we use an incredibly powerful algorithm called dynamic programming. The best way to picture it is to imagine a grid. Our template runs along one axis and the long recording runs along the other. Dynamic programming is all about finding the most efficient path through that grid, a path that perfectly stretches and squishes the template's timeline to find the best possible alignment.
And this is exactly why it is the perfect tool for speech. It doesn't care about finding an exact rigid match. Instead, it finds the path of least cost, which is the best possible way to warp the timing of our template word to fit into the bigger recording. This is precisely how your voice assistant can recognize a command, whether you say it super fast or really slowly.
So let's just step back for a second and look at the journey we've taken. We started with the simplest possible case, a pixel-perfect search. Then, we learned how to search smarter, not harder, to get a massive speed boost. From there, we made our templates flexible to handle real-world messiness. And finally, we took all those concepts from sight and applied them to the world of sound.
You know, in this age of giant, complex neural networks, it's pretty easy to overlook the power of these kinds of elegant foundational algorithms. But as we've just seen, they are the absolute bedrock of so much of the technology we use every single day. So the next time your phone unlocks with a glance, or you ask your speaker a question, you'll know about the simple, brilliant idea that makes it all possible. Thanks for tuning in.